Intro. This is a video on X-ray photoelectron spectroscopy or XPS by Adam Siegel, Alex Crawley, Hassan El Moussa, and Timoteo Diaz, material science and engineering undergraduates at Arizona State University, better known as the Science Migas. XPS is a material characteristic technique for investigating the elemental composition and chemical bonding states of a near-surface region of a material. This spectroscopy technique, also known as electron spectroscopy for chemical analysis, was first developed by K.C. Bond, which won him the Nobel Prize in 1981. The X-ray photoelectron spectroscopy, VG220IXL, is the model of XPS used in our lab to retrieve the data. Picture this is a picture of the XPS machine used for our experiment. Background in XPS: electrons are ejected from inner shell orbitals through bombardment with X-rays. The technique relies on light-matter interaction of the photoelectric effect, where the emission of electrons or other free carriers of light is focused on a sample, and in doing so, electrons are emitted, which are also called photoelectrons. The picture at the bottom of the slide is a diagram portraying the photoelectric effect. Elements of XPS. The main components of XPS are the X-ray source, energy analyzer, electron detector, and the ultra-high vacuum chamber. The inside of the XPS is held under ultra-high vacuum of approximately 6 to the -10th millibar. This low pressure is to prevent contamination of the sample and preserve electron energy by preventing collisions with gas molecules in the chamber. The X-ray source for this machine is aluminum. Monochromatic X-rays are generated at K-alpha 1.4866 keV energy. The electron detector detects photoelectrons emitted from the sample. How IT operates: XPS operates by having secondary electrons be emitted from the surface after they are excited by the applied X-rays. The secondary electrons are emitted from the first 5-10 nanometers, so sampling is limited to within the first 10 nanometers of the surface. XPS provides the energy resolution needed to detect elemental peak position shifts due to chemical state bonding formation. XPS can determine localized bonding chemistry of carbon and can differentiate oxidation states of inorganic compounds. Sample type. XPS is a very versatile tool with respect to what samples it can use for experiments. These samples include solids with low vapor pressure, thin films on solid substrates, very clean samples, insulators, polymers, and glasses.
I'm going to assume that we're in a good position. We'll take expected.
Because XPS is run at such a low pressure, no liquids can be used with this technique, as they would vaporize within the chamber. Procedure to begin the XPS experiment. The XPS must be at ultra-high vacuum of about 10 to the -10th millibar. This is achieved by 3 vacuum pumps consisting of the roughing pump, ion pump, and turbo pump, giving the 2 chambers the ability to reach ultra-high vacuum. The main chamber reaches about 10 to the -10th millibar, and the preparation chamber reaches about 10 to the -9th millibar. Reaching 10 to the -10th millibar does not just take overnight. On average, ultra-high vacuum takes around 3 days on constant pumping. The sample is inserted into the preparation chamber before it's pumped down to 10 to the -9th millibar. The main chamber's vacuum system is constantly running throughout the process, so once the preparation chamber has reached pressures close to the main chamber, the sample can then be moved using electron arms inside the microscope into the main chamber to begin testing. During the XPS tests, the sample surface is bombarded with X-rays or K-alpha particles, releasing characteristic electrons from the surface, which are analyzed by sensors within the instrument. From these measurements, further analysis can be performed using the CASA software. Sample investigation for our experiment. A 100 silicon wafer was deposited with a passivation layer using MOVD and then sputtered with copper and silver metal. We wanted to determine the oxidation number of copper on the surface of our samples for different annealing temperature. What info does XPS give us? XPS allows us to complete elemental analysis on our sample and determine the empirical formula and electronic state of the copper oxide. Spectrum analysis with CASA XPS.
So this is scanning through.
This is a live feed of obtaining the data, where the x-axis is the binding energy and the y-axis is the
Correct.
counts
So
per
you're
second.
all they're doing to do this is changing the setup.
XPS needs to be extracted into the CASA program. For example purposes, we will only be analyzing the 30-second anneal test run. Click on the 30-second anneal fold, copy all of the documents by double-clicking and dragging or Ctrl+A, and click Open. We open the periodic table and choose the elements that were used in the sample, which are carbon, oxygen, copper, silver. Then click on Find Peaks to generate model limits. After then we create simulated areas to estimate the area under the curve. Results as expected. Our sample contained copper, silver and oxygen. We were not expecting to find carbon in our sample. This contamination was most likely due to the microwave annealing following the sputtering process. Contamination was from the conventional house microwave used for annealing, and that our samples are old and have sat in air for an extended period of time. Obtain spectra data analysis. Figure 1 is a 30 seconds annealing wide graph of elements peaks. Figure 2 is a 30 seconds annealing elemental peak of carbon. Figure 3 is a 30 seconds annealing elemental peak of copper. Figure 4 is a 30 seconds annealing elemental peak of oxygen. Figure 5 is a 30 seconds annealing elemental peak of silver. Conclusion: this concludes our video and we thank you so much for watching. We hope you enjoyed it. The end.